In this video, we'll talk about the model that we're trying to develop, the notation that you'll find in a lot of machine learning algorithms and in other machine learning courses and books as well. Knowing this notation will make it easy for you to learn about machine learning from any other course or any book that you find. So before we talk about the model notation, let's talk about the data notation. So every data set that we work with has a number m of records. We also call it observations, signals, instances, data points. All of these are synonyms to the same thing. Each of those observations is a vector of features, independent variables, explanatory variables, predictors, dimensions, attributes. Again, all of these are synonyms to the same thing. And we will usually refer to all the inputs, to all the features that you have as X. And if your data set was a labeled data set, as in you were able to use it in supervised learning, we refer to that label as the target, the dependent variable, the response, or if this was a classification, you could also refer to it as classes or categories. And we refer to it generally as Y. So the output would be the Y, all of your inputs would be your X. So if you look at this data set here, the one we used in the previous video, we'll see that we have 30 records, which means that our M equals 30. We have two features, education and seniority, so the n number of features equals 2, and we have a target variable, which is the income in this particular case. Now let's forget about machine learning for a second and talk about something that we all know from high school math, maybe even before that, the equation of a line. Y equals mx plus b. The m here was your line slope and the b was your y-intercept, or the value of y where x equals 0. Remember, if you wanted to get the value of a y at any point in the x, you would multiply that x by the slope and you add the y-intercept, and that gets you a y. And if we do that for a couple of x points, we'd be able to find two dots that if we connect them together, it draws a line for us. So let's actually see that in Python here. I will just paste the snippet of code over here and I'll explain what that does. So what I have here is my variable x, which is a numpy linspace. The linspace function here returns an evenly spaced number of values between the start, the end, and this is the number of instances that I want. So it's essentially an array of 11 items between -5 and 5. Then I have a function that I'm creating here called plotline. Everything about this function should be familiar to you. The only thing that may look a little bit different than what you might be used to is the fact that I'm passing in a variable or a parameter called y, and I'm calling a function called eval with this value. Whatever this here evaluates to is being saved into my y underscore, and then I pass the value of it to my plotting function. So I'm still plotting the relationship between the x and whatever that y underscore evaluates to. Why am I doing this? I want to call the same function multiple times and I want to pass the value of y as a function. I want it to look like a function, like you'll see in a second here. So whatever string I'm going to pass into my eval function, it's actually going to execute it as if it was code, and then it will proceed the rest as it normally would. So let's see, if I do plotline y equals x, and I want this to be of the color red. Oh, I need to run this one first. Then we call this. Here we go. So now this is the relationship between x and y when y equals x. If x equals 0, so does y. If x equals 2, y equals 2. If x equals 4, y equals 4, so on and so forth. All right, so let's try a different line function here. If I plot 3x plus 5, and that will come out blue. So now at the value of x equals 0, my y equals 5. That's my y-intercept. So on and so forth. Let me just uncomment the other two lines here, which is -x plus 4 and y equals 2x. So for different values of m and y-intercept, or let's call it the slope and the y-intercept, we're able to draw different lines here. Okay, so back to machine learning. We've mentioned that for simple linear regression, the desired outcome of what we're trying to produce here is to draw a line. So essentially, we're trying to figure out what are the appropriate values for the slope and the y-intercept that would allow us to draw a line that best fits or best describes the data that we have. So in machine learning terms, or in machine learning notation, the formula now looks like this. Y hat, the predicted value of hat, we also refer to it as the hypothesis function, h of x equals theta of 0 plus theta of 1 multiplied by x. Thetas here are the coefficients that you multiply by the different features that you have. So if we wanted to generalize that so we can use it to represent a plane or a surface, then the function looks like this. The different x's that you have here are basically the different features that you have in your data set. That every theta is the coefficient that you multiply it by to get that outcome at the end. So let's see how we can diagram this here. So I'm gonna draw a figure here in a 3D projection, and the mesh grid here is kind of similar to the lens space, except that it returns a 2D array, so it's a mesh instead of a line. So my x1 and x2 are basically a grid from 0 to 10 in both directions. Here's my y hat, is going to equal 9. In that case, 9 here is my theta 0 minus x1. In that case, my theta 1 is actually -1, and same for x2. And so if I plot that surface, we will get something that looks like this. So far the math is holding for multiple linear regression. We're able to get a model. Essentially, if we're able to find that surface, that will be the model that we'll be using to predict any values of our target, giving the inputs that we have. So now the most generalized form of this multiple linear regression model would be y hat equals theta 0 plus theta 1 x1 plus theta 2 x2, so on and so forth, up until the n number of features. You could also represent this in the vectorized form. Y hat equals the transpose of my theta vector multiplied by the x matrix. If you're not familiar with this vectorized form, don't worry about it. It's just a different way to represent the same equation in a more compact way. I will say that unless you're developing your own implementation of the algorithm, you may not need to worry about a lot of this math. However, it is really important to understand how the model works, just so you can understand the results that you're getting. So again, to summarize the notations that we have here, x is basically the matrix of features that you have. Theta would be the vector of parameters that you have, so all the thetas would be your coefficients that you're multiplying your x's by. Y hat, or the hypothesis function, would be your predicted value. Alright, we're getting there. We know what is the final outcome that we're trying to achieve, and we know what the model will look like. Now we need to know how we can train that model, or how can we find the best values of theta, and we'll do that in the next video.